Actually, Jolian, would you do us the honor of muting everybody except for myself at the moment? We're just giving a few more people a chance to join us, so please ask for your patience. I want to welcome everybody to the 11th program of GemQuest. This one is specializing in sapphires. And it's been presented some very interesting challenges. Our co-host Jolian Ralph is a very talented programmer and a knowledgeable mineral guy, and who of course runs the mindat.org and the gemdat.org sites, which are the most visited gem and mineral sites in the world. And so for his help, we are grateful. This is a nonpartisan, nonprofit program whose whole intent is to educate and make interesting the subject of gems and gemology by specializing in one gem per month or one gem family per month. And as a point of information, next month we'll be looking at a different gem. We'll be looking at spinel, which is a very interesting gem and with almost as broad a spread of colors as our focus today, which is sapphire. Now, sapphire is an interesting gem, supposedly capable in the old writings of stopping people from being poisoned, but also giving people very good luck and power. And so it was always worn prominently by those who were fortunate enough, wealthy enough to wear one that was big enough to see. And of course, people who wore large pieces of jewelry obviously immediately communicated to anybody who saw them, they were people of power and position and wealth. So thanks to the popularization of gem cutting throughout the world, we were able to actually get a more widespread availability of gems than we've ever had in our history. And of course, what comes with that is a lot of fakery, mimicry, and synthesization of the gems that have value. And of course, sapphire is not the least of these. So today we had some interesting challenges in getting the program together because one of our speakers is in Bangkok and one was sitting on a mountain at his mine in Montana. And of course, our first speaker is coming from his home in Austria, and he's a very welcome guest in our program. He's joined us before and contributed very interesting information to help us learn and understand the scientific aspects of gemology, and today is no different. Dr. Clemens Schwarzenegger is a gifted fascinator and photographer and speaker. I see he's smiling modestly. He's also a researcher and associate professor at the Center for Scientific Gemology at Johannes Kepler University in Linz, Austria. And today, he's going to try and help us understand the very complex concepts involved in what causes color in sapphires. And I'd like to hand over the program to Clemens.
Thank you, Ray, for the kind introduction. Well, I was smiling because you gave me the name Arnold Schwarzenegger, which is also a fellow from Austria, but my muscles are a little bit not that well educated. I'm working a little bit more with the brain, or at least I try to do so. So let's start the presentation. And I hope that you can all see these wonderful colors of corundum, which I'm going to talk about. So the task that I was given is asking more or less a miracle from me to explain how the different mechanisms of color in corundum or general in minerals work, and this to be done within 15 minutes or something like this. So I apologize beforehand if I can't manage this with the exact time frame. So we all know corundum by itself is a colorless mineral, but you can find it on many, many places on the Earth and in almost every color of the rainbow. So we have here a couple of the classics. Of course, we have blue sapphires, we have the red rubies or pink sapphires, we have orange and purple, yellow and green within the same stones, and a couple of other colors here. So the question is now, where does the color come from? So in order to understand this, we have to get the presentation working, and we have to have a look at the crystal structure of the corundum a little bit. So in corundum, which has the formula of aluminum twice and 3 oxygens, so Al2O3, as we chemists call this, and the oxygens, which are the larger ions, they form a distorted hexagonal closed packaging. So it means that we have these hexagons, we have all of these oxygen balls, I call them balls now, they are connected by NH. And this is just one layer. So if we add a second layer on top of it, we add one ion on top of a hole, more or less. So it's in between 3 other oxygen ions of the layer that we have below. And we can go on and add up this second layer. And when we do this, we see that we have 3 red balls in the lower layer, and we have 3 of the golden ones, which are the exactly same oxygens on the top layer, and they form in between an octahedral void. And this octahedral void can now be filled with the cation, which is the aluminum. We fill up the second layer and insert now 1 aluminum here in one of these octahedral voids, and a second one in the second void, and every third void stays empty because of the stoichiometry that we have. And then we fill up a next layer with the aluminums. Here we have 1 on top of the position where 1 aluminum is in the layer below, and the next one is on a layer where in the layer below is no aluminum. So we do not fill always the same voids with the aluminums, but they are rotating more or less. So every 2 out of 3 voids are filled with this aluminum. And if we now just have a look at the corners or the centers of gravity of the oxygens, they will form these octahedrons. And these octahedrons can be combined via the edges or the faces. And if you look at the larger selection, then you will see how a crystal is formed. What is not correct in this drawing is that the oxygens are small and the aluminums are large. In reality, it's the other way around. We have large oxygen ions and we have very small aluminums and in general cations that are in between. So this is the material that we all know under the name corundum. And as all of the shells of these ions are fully filled or completely empty, so the highest shell is always, I call it a sealed shell, there is no single electron that can be excited, and there is no color at all in the visible range. If we look a little bit closer into the distortion that we have in this lattice, then we have these 3 oxygen atoms which form a triangle, and on top we have the next layer which also forms a triangle, but in this case the distance between these oxygens is a little bit smaller than in the lower layer, and the aluminum, which is here in the middle, is a little bit shifted towards the lower layer. So it's not perfectly symmetrical, but we have a distortion. And this is very important to understand the color and the different optical properties of corundum when we look at it at different angles. So the first thing that we need in order to get some color is we need some free electrons, and we need electrons that can be excited. And in order to have electrons that can be excited, they must have the perfectly right energy to be shifted from a ground state to a higher state within the visible light range, which is the 400 to 700 nanometers. And we just have to look at these elements which are written here in the periodic table of elements, which are titanium, vanadium, chromium, manganese, iron, and cobalt. There are a couple of others which might play a role in mineral colors as well, but these couple here, these 6 elements are making up for more than 90% of the color causes that we know, because they have the so-called d orbitals, and in these d orbitals there are some electrons which are not paired and therefore can be rather easily excited within the energy that we see in our visible light. So titanium, vanadium, chromium, this is mostly the material that you need, and some iron is also important for our sapphires. So today I'm going to talk you through 3 different mechanisms of how color can be brought into minerals. And the first and easiest to understand is just through the excitation of electrons. So we have to start with the chromium. Also, you might say, well, if we put chromium into corundum, then we don't have a sapphire, we have a ruby. In fact, this is the perfectly physical explanation that there is no difference between a pink sapphire and a red ruby, except the concentration of the chromium that you have. And I always tend to say it's a question of selling or buying. If I'm selling something, it's a red ruby. If I'm buying, it's just a pink sapphire. So this is the big difference. What we have is chromium, and the chromium in its trivalent state is a 3+, and it has the configuration of electrons, which we call 3d3, which means we have in the 3rd layer, we're talking about these layers, you might remember from basic chemistry, and the d orbitals, where we have 3 electrons, 3 unpaired electrons in the d orbitals. We have a ground state where all the electrons are when nothing happens. And we have the possibility of an excited state when some kind of energy is absorbed by the electron. In this case, it's our light. It's the visible light that we have. And if the energy is perfectly right, then we have an excitation of an electron from the ground state into the excited state. And it means that the energy which is necessary to lift the electron from this to this energy level is absorbed from the white light, from the spectrum of the white light. And what we see is a so-called absorption spectrum, where we have everything passes here, everything passes until we have the right energy to lift our electron to the excited states. Then we have absorption, no light comes through. And then if we have, in this case, lower energy, nothing is absorbed again. So what we will see with our eyes is that in this case, greenish, yellowish part is absorbed, and we have passing of blue and red. So the color that we would see in this, whatever mineral it would be something like a violet or a purple. We have a mixture of blue and red. So this is rather easy to explain. Simple, we need just an element that has a free electron, and this free electron can be excited to a higher level. And if this energy is within the visible light range, then we have somewhere here an absorption band, and this color is not to be seen. What we see is the complementary color, which is the remaining of the spectrum. Okay, so now I have to destroy a couple of your things that you learned in school, probably. We were talking about electrons, and most of you have learned the model from Niels Bohr, where we have these shells, and we see this is the innermost shell, where we have the first layer of electrons, then we have the next shell, the outer layer of electrons, and the third one, and again and again. So we were talking about electrons spinning around the nucleus, and they are more or less on these circular or spherical shapes. Well, unfortunately, this explains a couple of properties that minerals or that in general elements do have, but it's not true at all. What we do need for today, and this is a little bit more tempting material that I'm trying to explain, is we need orbital theory. So orbitals are the areas where you most probably find an electron. So an electron cannot be localized perfectly, but you always only have a probability where you can find it. And if we're looking at the so-called d electrons, that's the one that we have in chromium, we see that we have 5 different shapes of orbitals where our electrons can be found. So 3 of them are rather easy. It's the dxy, dyz, and dxz. You don't have to remember the names. It's just the d stands for the type of orbitals that they have, and the rest is the orientation. So you see they're in between the geographical axis or the crystal axis that we have, these three, and we have one, the dx squared minus y squared, which is perfectly along the x and the y axis, and we have dz squared, which is my absolutely favorite orbital because you have this nice shape here with the donut around it, and this is along the z axis. So this is important because we now know that our chromium in this case sits in between 6 oxygen atoms, and these oxygen atoms interfere with these orbitals. We have here, for example, the dz squared orbital, and you see the oxygen atoms. The oxygens have a negative charge and the electrons are negative. So in the direction of this z-axis, we have the negative charge of the oxygens pressing in here into this z-axis, and therefore we have a different energy level here than we would have in the direction which is in between all these oxygens. So this leads to a distorted field, to a so-called crystal field. And this crystal field now brings us that we, in a free ion, have 5 equal d orbitals, and these equal d orbitals are now split up in 2 orbitals. You see the dz squared and the dx squared minus y squared, which are perfectly along the x, y, and z axis. Therefore, they have a higher energy because electrons are negative, the oxygens are negative, so they have some pushback mechanism and the energy is increased here. On the other side, the d orbitals, which are in between the oxygens, they have a lower energy. So instead of having 5 equal d orbitals for the free ion, when the chromium is in a crystal field, which is a crystal lattice in all of the explanations that we use, then we have a splitting of different orbitals and therefore different energy levels. And this is different if we have an octahedral field, a tetrahedral field, and it depends also on the shape of the field. Here we have the oxygens along the z-axis pushed together a little bit. You see here these delta minuses pushing towards the electrons, and therefore you have a shift in the electron level or in the energy level. And this is, for example, a simple explanation why chromium in some minerals appears red, and in some others, like in emerald, it appears green, because the crystal field is different. The crystal symmetry, the oxygen atoms that are neighboring our chromium are pressing harder or less hard onto the electron shells, and therefore we have different absorption levels and different absorption colors. So this might look a little bit weird, but it's a wonderful explanation given by Kurt Nassau in his book, The Physics and Chemistry of Color. And it helps us to explain wonderfully why we have the absorptions in pink sapphire or ruby that we see. We have here a so-called term diagram where we have the ligand field, which is just a measure of the symmetry or the shape or the distortion of the crystal field of the oxygen atoms that we have, or oxygen ions to be precise. And we have the different energy levels that the chromium has. So these chromium energy levels are here represented by these lines. We have 2 different lines here for the 2 different term shapes, which I don't go into details because I think this would lead way too much into the physics. But you see that you have these lines are depending on the ligand field of the strands of the ligand field that you have, and there is a value assigned. So when we cross here the ligand field of the chromium in a ruby, we see that 42 level is a little bit above 2.2 electron volt, and we have, if we look here, an absorption. If we go to the second absorption table, we are at 41, we are approximately at 3 electron volts, and again we have here the absorption. What you might see more frequently is the middle term here, where we have a ground level, we have some excited levels where the electron can jump up to or can fall down to, and these are exactly these 2 transmissions that are possible in the absorption. We can absorb from the ground level to this 42 level or to this 41 level, and these are the 2 absorptions that we see in our visible light. So we have an absorption in the violet part, and we have an absorption in the yellow-green part. What remains is the transmission here in the blue, and in the red. And if you look closely, you see that the transmission in the red goes to 0 energy. So red is completely transmitted, and the blue does not go completely to 0, but we have sort of a lighter blue shade. So this is why a ruby generally has a red and a bluish red color. What I just want to mention here briefly and not explain in details is the fluorescence, because what happens to the electrons once they're excited, they cannot stay in the excited level, they have to come back to the ground level. And unfortunately, physics tells us that it's not possible to fall down on the same way that they are excited. So they have an intermediate level, which is here the 2e level, where they can be removed at. So by creating some heat, they come down to this E level, and from this E level now it's allowed to go down to the ground level just very slowly, and this slow emission of color in this case is what we see as a fluorescence. So if we heat, if heating is not the right word, if we have any light source that has a higher energy as one of these two levels, the electrons will be pumped up, fall down to the E2 level, and from E2 level, they give us this nice red fluorescence of chromium in ruby at 692 nanometers approximately, which is the strong red fluorescence that we see when we shine, for example, with UV light onto this ruby. So this is the first mechanism that gives us one of the most prominent colors that we have in corundum, the pink to red colors of the chromium inside an aluminum oxide. The next mechanism we're talking about is the so-called intervalence charge transfer, or short IVCT. So intervalence charge transfer means that we have a transfer now from one electron from one atom to another atom. This can be either from the same type of atoms, like from an iron to an iron, but the most prominent one here is from an iron to titanium. So in the general state, we have iron as a 2+ ion, and we have the titanium as a 4+ ion. Now, if we have light of the proper energy, then one of the electrons from the iron is transferred onto the titanium, and both end up at 3+. So we're electrically neutral. We just shifted one electron from here to here. And of course, one prerequisite is that the iron must be neighboring the titanium. So we cannot shoot the electron across large distances, so they must be proximate to each other. And again, this is a mechanism where an electron changes its energy level, therefore we see some absorption. Here we have two different cases. We might have two of these octahedrons, these oxygen octahedrons, which are connected via one phase. So 1, 2, 3 triangles are shared by these two octahedrons. And then we have here the iron, here the titanium, and the distance in between these two ions is 2.65 angstroms. So angstrom is a measure that we use in chemistry, because a lot of bondings and atom sizes and ion sizes are in the range of angstroms, and it's easier to explain everything instead of having nanometers, micrometers, and whatever. The second case that we have to look at is if two of these octahedrons are connected via one edge. In this case, we also have the neighboring iron and titanium, but the distance is a little bit further away. They are 2.79 angstrom. Not that much of a difference, but a big difference in energy. And the difference is that in this case, where they're closer together, the orbitals are overlapping more than here. And if the orbitals are overlapping more, then it's easier to have one electron jump from here to here than when the orbitals are not overlapping that much. Therefore, this charge transfer is easier and is more prominent than this one. So why is this important? Because if we look at the crystal of corundum, we have the C-axis, and along the C-axis we have this type of packaging, whereas in the AB axis we have this type of packaging. And this explains perfectly why we have a dichroic material. So if we look along the C-axis, we will have the so-called ordinary ray, which is very, very color intense. And the extraordinary ray, which is in the AB direction, is typically much paler than the other one. In some cases, it can also have a completely different color. So here we have the UV-Vis spectra, and we see the absorption that is created by this iron titanium IVCT. And we have here the ordinary ray. We have a strong absorption at about 560 to 580 nanometers, which means that here all of the light is absorbed. Visible light is from about here, 750 to the 400, and the 400 is the blue. So we have a transmission in the blue, and we will see an intense blue color. If you look at the other direction, the E-ray, for example, here we see that this mechanism is the same. We still have the iron titanium charge transfer, but the intensity is much, much lower here. And therefore, we do not have that intense difference between the transmission window here and the other regions of the spectrum. And therefore, the color is more pale or might have some yellowish or greenish overtones to them. The third model is probably the most complex one, and I will just touch it briefly because Dick Hughes has it in his book, and I think most of you who are interested in rubies and sapphires will have this book. I use it today exactly as a very important task because it's carrying my laptop in order to have it a little bit higher here. Wonderful to have these huge books. And it is more like an extension to the charge transfer, because in this model, we look at the aluminum oxide as a semiconductor. And in the semiconductor, we more or less say that we have a valence band, which is something like an energy level. It is an energy level where we have all our electrons inside. At room temperature, all of the electrons in a semiconductor are in the valence band, but we have a conduction band, and we have in between something like a forbidden zone. If electrons are excited into the conduction band, then electrical current can be transported. In our case, this is not of interest because aluminum oxide is a nice insulator, and we just don't want to transport some currents or some voltage, but we want to see color. So there are a lot of elements that have energy levels inside this forbidden zone. And this leads to the possibility that electrons can be excited from one point to the next, to the another, like the vanadium ion, and then to the conduction band. And if one of these two energy gaps is within the light, the visible light source, then we do see color. So that's the easy part. However, we have to know the exact chemistry in order to predict the color that we will see, because like titanium is a very high level here, and magnesium is a very low level. And if we don't have silicon, for example, which would be even above the titanium, we will always have titanium, which pairs with the magnesium into a charge transfer. However, this energy is larger than the band gap that we have in the visible light, so we do not see color. What we see is the titanium to iron transition. So the problem now is, as long as there is magnesium, titanium will pair with the magnesium and not with the iron. So you need to understand the complete chemistry that in the first step, titanium will pair with magnesium, and only if the concentration of titanium is larger than the one from magnesium, there's titanium left to interact with the iron. And only if you record the concentration of all these elements, you can see how the charge transfer acts. And if there is titanium and magnesium, you have to measure both concentration to create the free or active titanium. And you have to have the iron and a couple of other elements to see what is left in transition elements that can undergo these transitions. And with this, I hope I could explain you the three most important causes for color, not only for corundum, but for almost all of the minerals that we have. And especially for corundum, we have a couple of elements that we know, which we can 100% assign to color, which is for the chromium, for example, the red and the pink color. Chromium needs about 1% to create a ruby. If it's lower, then we talk about pink sapphire. The blue is generally created by iron 2 titanium 4 charge transfer. In this case, it's important to see that this is much more potent as it only needs a couple of ppm. Only parts per million of titanium and iron need to be present in order to have this color mechanism. You always have iron 2, iron 3 charge transfer, which is at 880 nanometers. This can be used, for example, to differentiate between the metamorphic sapphires and the other sapphires. Some have a high amount of iron, some have a low amount of iron. We have orange sapphires, which are due to chromium in many cases, but might also be magnesium. And here we talk about holes, oxygen. The background is we have magnesium 2 plus sitting on the place of an aluminum 3 plus. So in order to be electrically neutral, we need to change the charge of the oxygen from 2 minus to 1 minus. And if we have a 1 minus, we have a single electron on the oxygen. And this is also a very potent light absorber. So the oxygen hole is responsible for a lot of color that is going on in sapphires. And together with the magnesium, it produces intense orange color. Intense yellows can be found when we see iron 3 plus these oxygen holes. If we only have the iron 3 plus, we have pale to medium yellows. Grayish blue to green can be created by vanadium. Also, all of the color change varieties typically contain vanadium. And we can also interfere a little bit, being a scientist or being lucky in this case. Some people by accident found out that if you heat the sapphires in the presence of beryllium minerals, the beryllium is diffused into the lattice and interacts with a couple of those other elements and creates intense orange sapphires. So these are the most colors that you will find in your sapphires. Here's a couple of examples that I have in my library, I would say. And I'm sure that Dick and also Warren will give us some more details on how they are found and how they are treated, and maybe also how the fraud is going on there. Well, this is the end of my presentation. I hope you understand a little bit more about the color in sapphires today. And if you have any questions, feel free to ask. I'll do my best to answer them. Thank you.
Thank you very much. I appreciate that. That was a very complex topic that you brought, hopefully to a level that some of us will understand. If you want to stop the sharing, that would be awesome. And just to bring it to a small question to you, when there are different geological environments, so there are 2 or 3 different major environments that the corundum forms in. So is it the qualities of the magma or the host rock that will determine what percentages of iron or other coloring agents are in there, and can it change during the crystal formation due to leaching or infusion from the surrounding waters?
Oh, that's a tough question for somebody being not a geologist. So of course, the surrounding plays a major role in the crystal chemistry that we have. All of the magmatic sapphires have a high amount of iron.
Yeah.
If this is leached out, I don't know. However, the amount that we're talking about is so much higher than the metamorphic sapphires that you probably have no chance by leaching to reduce this high iron concentration to an amount that would be typically for the metamorphic ones.
So the matrix rock then will have a strong determining factor as to what color you're going to have, because they're going to be controlling or limiting the amount of ions that are available in the formation stages.
Yeah. And as you have seen in these band gaps, there's a lot of elements that can interfere with color. And this is one of the problems. You cannot only measure 1, 2, 3 elements, because you have to understand the complete chemistry in order to rule out several color origins, or in most of the cases, the question is, where does the sapphire come from? And this can only be done if you have a complete chemical picture, if you have a complete inclusion picture, if you have all the information that you can lay your hands on.
So I guess this is one of the reasons why you need a really good cutter if you want to maximize color, because they're going to be able to determine which axis they need to cut on to maximize the color from the crystal they're cutting from.
Yes, 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 of course. If you have the perfect crystal, it's easy. You just have to determine, do you want it brighter or darker, cut it in the sea or not the sea. However, if you look at sapphires like from Sri Lanka, then you might you might run into the problem that most of the crystal is colorless and there's just a small rind of blue on the outside.
Yeah.
And then you have to find the best way to concentrate the color in your culet, because in the culet you have the reflection that goes throughout the finished gem.
Yeah.
However, this ends up in the shapes that we all know from Sri Lankan sapphires being extremely deep, because we have these bipyramidal crystals. You cut them in the middle, you have the culet down in the tip, and then you have the long crystals with huge pavilions. Yeah. You need a cutter to understand how the process is working, but still there is some room for optimization, because unfortunately still everybody pays by the carat and not by the beauty of the gems. And as long as people are paying by the carat, you will have cutters that, well, they know their job, but they make use of the physics behind this.
They cut for weight.
They cut for weight, yeah.
Yeah. So I mean, that's the difference between what the derogatory comment about cutting with, oh, that's a native cut versus a professionally cut stone, because the native cuts are often, because of the nature of the business, going to be cut for weight and not for aesthetics. So yeah, thank you for your insights. Does anybody else have a question they want to put to Dr. Schwarzenegger before we move on? Either you confused the hell out of everybody, or you really informed everybody very well. Thank you so much. I appreciate it, Clemens, and thank you for giving us your time to put together this presentation. I know it was a complicated challenge.
Thank you for inviting me. Always trying to give my best.
And you do.
Thanks.
Thanks. Okay, Julian. Are you there, Julian?
Yes, I'm here.
Okay, just before we move on to the next section, I'd like to explain to everybody a few things. To put together this program this month, we had to travel the world effectively and across time zones that were inconvenient for actually showing a live presentation, as we just did with the Dr. Schwarzenegger. So they were recorded. And in the case of the next speaker, Mr. Boyd, he was recorded on the top of a mountain in the middle of Montana using a satellite. So I'm going to apologize to you ahead of time, because there are some cutouts and some awkward frozen moments because of the satellite transmissions. But if you will be patient with us, you'll get some interesting things from our next speaker. Our next speaker is Warren F. Boyd, and he's a fellow Canadian. He's a gemologist and a geologist. I knew his father. His father was the preeminent opal dealer in Canada when he was alive. And I know that Warren still has some of the stock of opals from his dad's business. And his dad actually was one of the founders of the Canadian Gemological Association. And following suit, Warren was also a past president of the Canadian Gemological Association, and is presently the vice president of the International Colored Gemstone Association. So he's a man that straddles both sides of our industry, the geological and the gemological. He has worked in the field with diamonds, colored stones, and sapphire deposits, and is presently working with the Potentate Mining Company, which is a sapphire mine site at Rock Creek, which is locally called Gem Mountain. And I can say I've done some panning at the commercial public end of Gem Mountain for sapphires. And it is the largest producer of sapphires in North America, and definitely the largest one in Montana. So it's located near Phillipsburg. And so what we're going to do now is move forward using a pre-taped presentation that we taped at the house on the mine site. So we're really stretching the limits of connectivity here, and I hope you will bear with us and be patient. So Julian, if we can move forward with Warren's program.
Yes, just to mention that we actually recorded this yesterday, so we haven't had time to edit out the glitches. I'm sorry about that. Okay, we're ready to go.
All the way from remote camp in Montana. We're very fortunate, again, as I said, to have our guest speaker, Murray, to tell us a little bit about the geology of sapphires.
Yes. Actually, it's Warren.
Warren, what did I say? Sorry about that.
Murray.
Oh, good grief.
Yeah. It's like Biden.
Yeah, thanks. I'm probably the same age too.
Okay, so start in there, Ray.
We might want to edit that part out, Julia.
Well, Ray, I appreciate the invitation to talk to the group and to educate my fellow gemologists and any geologists who join us on the nature of sapphire deposits. It is a complex topic. There are many types of deposits of sapphires around the globe. The geology and geochemistry varies radically, as can be seen in the quality and the look of the stones that come from different localities. But in general, sapphires occurrences can be broken down into two major categories. First of all, a primary deposit, and secondly, a secondary deposit. So primary deposits, these are deposits can be broken down to a number of categories within primary. The first category in a primary deposit would be a magmatic origin, and the second category would be a metamorphic origin. And to give you some examples of sapphires in a primary deposit, like the magmatic deposits, that is, they can occur in basalts and lamprophiles. And a basalt occurrence is examples of sapphires coming from Australia, Thailand, and Nigeria, and China. They're a very particular type of sapphire that are quite distinctive. Secondary magmatic deposits are the lamprophere. I believe, and most people concur, that most of the sapphire deposits in Montana come from a lamprophytic origin. Now, the second category in the primary deposits of sapphires would be metamorphic. And these are sapphires that occur in hard rocks in marbles, such as mogok, in skarns, alteration zones, and in pegmatites. Now, we've alluded to the fact that these are the primary deposits, but the reality is that most sapphires are mined in the world from secondary deposits. And the secondary deposits can be broken down into four major categories. There's illuvial, and that's spelled with an E, E-L-U-V-I-A-L, illuvial. And that's where the sapphires are weathered from the bedrock, simply sitting on the surface and right near the bedrock occurrence or in the weathered bedrock. Second is a diluvial occurrence, which is D-I-L-U-V-I-A-L. And these are scree or talus slopes coming down from a mountain side. For instance, the original Kashmir sapphire occurrences were in Tanzania, where the host rock is questionable, like the Tonduro sapphires and Songea sapphires. There's not much geological literature on the host rocks, the original rocks, which I do not think are preserved. So all the sapphires there are mined in alluvial environments.
So these alluvial environments you're talking about, I'm assuming are all old deposits, are not current riverbeds like we do see with some of the mining in Africa for diamonds.
Ray, could you repeat the question? I think I lost it there.
Okay, well, I'm assuming from what I've seen and what you've told us that most of the alluvial deposits in the world that are being mined are old buried alluvium and they're not present riverbeds that are active river systems like they do with diamonds in Africa.
That's true. The bulk of the sapphires in the world are mined from alluvial deposits and colluvial environments.
But they're old
conversely,
ones.
Yeah, conversely, the bulk of diamonds mined in the world are from kimberlite pipes, with a minority coming from alluvial environments.
But the reason I was asking is, are there any actual live present day riverbed mining of sapphires that you're aware of? I mean, it seems like all the mining is old riverbeds that have long since been buried.
Sri Lanka, when I was there a few years ago, I saw them collecting, mining using like a sophisticated rake that 4 or 5 guys will pull through to rake up the gravels and look for the sapphires.
All right. And in your mind, what are the best types of deposits for getting a good yield in sapphires? Oh dear.
Your question?
I said, in your mind, what are the best locations for mining sapphires? In terms, I'm assuming the one you're in right now must be one of the better ones.
Well, that's probably why I'm here. I first.
Oh, geez.
With what I saw, that operation.
We missed all that. I'm sorry.
Yes, I mean, by North American standards, I think this is the larger deposit in Montana, and Montana as a state is known for producing sapphires from 4 different localities, 3 of which are alluvial, colluvial, and only 1 is hard rock.
Yeah. I'm assuming the yield from the colluvial alluvial gives you stones that have already been pre-beaten up by the process of erosion, and therefore a much easier yield than those that have been taken out of hard rock.
It is always more expensive mining any product from hard rock than it is mining weathered bedrock. For us, we're mining no more than 15 feet deep, and we process the material in jigs and collect the heavy mineral concentrate, which includes the sapphires.
I met a guy who was actually working out of gravel beds, not even diamond and not even gem bearing beds, and they were using a special machine to recover gold flour from the mining. So they actually had a side profit from doing that. I'm wondering if that sort of thing is happening where you are.
Yes, that's not uncommon. In fact, we have what we call a sweetener in fine gold. We use in all the muddy water from our jigs is diverted into what's called a centrifugal concentrator. Our brand name is IG. It's a centrifugal concentrator, and we spin it at very high speed and then recover the very fine gold. Our operation does produce gold, but it's a minor component. We couldn't run our operation on gold alone. It requires, and we treat gold as a sweetener.
Well, look, I appreciate your having helped us out here, Warren, because yes, these are trying conditions, and you're in a remote area. So I'm so excited that we actually got to talk to you and hear some of your expert knowledge about the geology of sapphires. And I hope you have a great day, and we'll look forward to seeing this your contribution in our program tomorrow. Thanks very much.
Of course.
Sorry.
Of course, Ray. Thank you very much. And if anybody has any questions, I can always address them through a follow-up later, and you can provide my contact information for that, Ray.
Okay, well, if you want, do you know what your email address is, or do you want that to be given out?
Well, I can give it on audio, sure. It's Warren F. Boyd. That's WARRENFBOYD, hotmail.com, or Warren at potentateMining.com.
Yeah. Well, look, that's awesome. Sounds like you've got a beautiful day there, and I'm hoping we will tomorrow as well. So have a great day. Thanks for your contribution, Warren. It was very much appreciated to help us understand a little bit better of what goes on behind the scenes before things get cut and when they're first being discovered. And you are at the forefront of all of that. So thank you for being a part of the program.
Thank you. You're
Thanks for
still-
making that happen, Jolian. It was obviously a little bit difficult. So our next presenter is the world famous Richard Hughes. He's considered to be the world's foremost expert on rubies and sapphire, the author of several books and over 170 articles. His writings and photographs have appeared in a diverse range of publications, and he's received numerous industry awards. Co-winner of the 2004 Gubelin Most Valuable Article Award from Gems and Gemology magazine. The following year, he was awarded the Richard T. Litico Journalism Award from the American Gem Society. And in 2010, he received the Antonio C. Bonanno Award for Excellence in Gemology from the Accredited Gemologists Association. The Association Française de Gemologie in 2013 named him as one of the 50 most important figures that have shaped the history of gems since antiquity. Wow. And in 2016, Richard was awarded a visiting professorship at Shanghai's Tongji University. And in 2017, saw the publication of Richard and his wife and daughter's Ruby and Sapphire, a Gemologist's Guide, a book I recommend to you, obviously. Arguably the most complete book ever published on a single gem species, and the culmination of almost 40 years of work in gemology. And then furthermore, in 2018, Richard was named the Photographer of the Year by Gem A, recognizing his photo of a jade trading market in China, while in 2020, he was elected to the board of directors of the Accredited Gemologists Association and was appointed to the editorial review board of Gems in Gemology and the Australian Gemologist magazine. His latest book, Jade, a Gemologist's Guide, is scheduled for publication next year. So without any further ado, and of course I will add, we did have occasional blips since this was dependent on the internet system in his area where he lives in the Far East. We now will hear from Richard Hughes, Dick Hughes. Jolian, if you could present that video, it'd be appreciated. There you go.
Okay.
Well, first of all, having already introduced you and established that you're a demigod of the gem world, I'd like to move into a sort of an interview format, if that's okay with you, Dick.
Sure.
And,
Fire away.
and some of my questions may seem simplistic, but not everybody in our audience is a gemologist. And for that matter, the geology part will be handled by a geologist. So we're really looking at basically a gemologically based discussion. And although it may, as I say, may seem simplistic, the first question I wanted to throw at you, knowing that you know everything about this subject, is to someone who is not knowledgeable about gems, how would you differentiate between sapphires and rubies, knowing they're all corundums? So if someone wanted to be absolutely sure they're not looking at a pink sapphire, they're looking at a ruby, what's the differentiation between rubies and sapphires?
Well, as you know, the mineral is actually named corundum. And so the difference between a ruby and a sapphire comes from early times when people didn't know that they were the same mineral. And so they gave the red ones one name and they gave the blue ones a different name. In fact, there is very little evidence that there was ever rubies in ancient times. The things that people called ruby 1500 years ago, 2000 years ago, were either garnets, or a little bit later, they were red spinels.
That's correct.
And so ruby is actually a relatively recent find. There's a couple examples going back in ancient history, but nothing to speak of. And so as mineralogy got going in the 1700s, 1600s, particularly as analytical chemistry developed, then people started looking at these different minerals, and they found that, lo and behold, the thing they called sapphire and the thing they called ruby were one and the same. And they were just different color varieties of the same mineral. And so how do you separate ruby from sapphire? Well, that's a question that bedevils gemologists even today, because it's very hard to describe color. And so everyone is in general agreement that ruby is red. However, in the English language, and in other languages too, but not all of them, we segregate a red into two different colors. So the deep reds, which is down here, I don't know if you can see my mouse pointing at this or
Yes,
not. So the deep reds we call red, and then the lighter reds, lighter in tone and saturation, we call them pink. Interestingly enough, in the Thai language, and also in a couple other European languages, they do the same thing for blue. And so if you ask a Thai person, what color is this here, they would say si fa, which means a lighter blue. And then if you ask them, well, what color is this? They'd say si nam ngan. And so they do the same thing that we do in English for pink and red. So a deep blue is a different name than a light blue. And so because of these kinds of things, it makes it extremely difficult. Descriptions of color are often cultural based. For example, the Eskimos, because they're dealing with ice and snow, they have dozens of words for the different colors of ice. The Indians in the Amazon jungle, because they're in an environment surrounded by green, they have many different words for different shades of green. And so it's hard to apply one single definition across the globe, because these things are often cultural based.
To the uninitiated, Dick, and I've asked many this way because I'm a jeweler, they all believe that sapphires are all blue. And is there any, could you just take a moment to let us think about how many different colors there are that constitute sapphires?
Yeah, well, in the old days, they used to call something with a prefix Oriental. So the Oriental sapphire was what we call a blue sapphire today. The Oriental topaz, which is like these stones here, is what we would call an orange or yellow sapphire. Oriental amethyst was a more violet sapphire. They used the prefix Oriental because that meant it was harder. So an Oriental topaz was harder than a regular topaz. An Oriental amethyst was harder than a regular amethyst. And eventually that terminology fell by the wayside as mineralogy got more and more precise. And it was, I think, in 1798 that Count de Bernin for the first time really identified corundum as you know, Oriental sapphire, Oriental ruby, Oriental topaz as all being the same mineral. And he chose the name corundum because it was derived from a Sanskrit word for a very hard stone that was being used in southern India.
Oh, thank you. Across the world, there are numerous countries from which we have excellent quality sapphires coming out. Could you take a few minutes to talk to us about the different locations and mining areas across the world where the main groups of sapphire have been found? And if possible, is there certain sites that are known for certain colors more than others?
Yeah, I mean, in the ancient times, talking about blue sapphire and yellow sapphires, the source was Sri Lanka, Ceylon or Serendip, depending on what you want to call it. And even in Roman times, there was trade between Sri Lanka and Europe. And one of the things that was traded was sapphires. Interestingly enough, we don't have rubies showing up. And that really tells you that there weren't any major quantities of ruby in Sri Lanka, and that continues to this day. So we really don't have rubies showing up until maybe 700, 800 AD, that kind of thing. So Sri Lanka was the original source of sapphire. And then they also found blue sapphires in Burma, in the Mogok area. Now it's called Myanmar. And so there were two major sources of sapphire, if you talk about going back 500 years ago, Burma and Sri Lanka. Those were the two sources. As time went on, they discovered other sources. In fact, there was a source in Europe, in France, going back, again, 2,000 years. But these stones were a very dark color. And so it was not the ideal type of material like you would get in Sri Lanka or in Burma. So these basalt-derived sapphires were found in France. They've also been found in a number of other places, Australia, China, Thailand, Cambodia, and more recently in Nigeria, in Rwanda, and a few other places, southern Vietnam. And so those are the major sources that produce most of the material. They have found sapphires in the US state of Montana. And generally speaking, some of the Yogo sapphires are very nice, but the sizes are very small. It's a rare day when they find a stone that can cut 1 carat. Other places in Montana, like Rock Creek, are very rich in sapphire, but the colors are not as nice. And then in the 1870s, 1880s, they discovered sapphire in a remote area of northern India in Kashmir. And the quality of those stones was so remarkable that people haven't stopped talking about them ever since. The main production from Kashmir took place over a very brief period, surprisingly enough. About a 10-year period was when most of the material came out. Since that time, they've tried to find more, but the quality is not the same as the original pockets that they hit. And so those stones are the most valuable blue sapphires today, and they fetch a huge premium because of their quality and because of their rarity. The Kashmir stones have a velvety blue color, and let me just scroll down here and I'll show you some examples. So you'll see what they look like. Just bear with me here. This is an inclusion in a Kashmir sapphire, and you can see this soft texture that the stone has. And so that's what they're famous for. And here you can see examples of some rough and cut stones. They have this velvety appearance. There's a very fine particle inclusions inside the stones, and that's what makes them so famous. It's a very soft color, and those fine inclusions scatter the light around the stone, and they cover up the areas that are normally very dark. Now, in recent times, in the 1980s and 90s, particularly in the 2000s, another source came online that has become very important, and that is Madagascar. And Madagascar you can see this is a Madagascar sapphire, and you can see it has that same soft velvety appearance of a cashmere stone. And so these have become highly desirable. They also find a lot of fancy sapphires in Madagascar. I'll show you some. Here's a parcel of rough, and you can see this is in the Alakaka area in southern Madagascar. They get a lot of pink sapphires, yellow sapphires, some orange sapphires, paparachas, and they also find rubies in Madagascar. So it's become a huge, huge source in recent times.
You
So
did
those
slip,
are the big sources.
thank you. You did slip in a few of those trade names that are special for color that add value to the stone. Could you just take a few minutes to share with us the most valuable colors in sapphire and what their names
Yeah.
are?
Sure. Let me just bring up a page that shows those. Here you can see the different color types of ruby and sapphire. These have become very popular among gem dealers and buyers, and it's one of the biggest sources of argument among gem dealers and lab gemologists as well, because color is so hard to describe. For example, you have the paparacha sapphire, which is a mixture of, it's basically a mixture of a ruby and a yellow sapphire. And it's that mixture creates a kind of a pink orange appearance. And that is next to blue sapphires and rubies, that's the most valuable variety of corundum. You have some others like this. This is a Thai sapphire, and it's a kind of a whiskey color. So they call it after the local whiskey, Macklong whiskey. That's another type. But to give you some idea of how difficult these things are to describe, for example, paparacha sapphire, what constitutes a paparacha sapphire? I did a little survey a number of years ago in Sri Lanka where I put a color chart on my iPad, and I asked various dealers to circle the areas that they thought included the paparacha color. And these are just 6 examples here, and you can see there's no real agreement. And you know, if you asked dealers to tell you what is a pink sapphire and what is a ruby, you'd have the same problem. And so it's no wonder that laboratories cannot be consistent in describing these things, because the people who handle the most stones themselves, the dealers, they have no consistency in what they believe constitutes a paparacha or a ruby or a pink sapphire.
Obviously, it's to the dealer's advantage to be able to make those claims and therefore get more money for the materials that they're selling.
Yeah, and at the same time, they want laboratories to put these terms on the reports, and then they're upset because the laboratory's ideas of these things does not match their own. And you know, you've been in the trade a while, you know, it's the old saying that, you know, is it a ruby or a pink sapphire? Well, it depends on if you're buying it or selling it.
So within the cutting of sapphires, there obviously are 2 major forms, cabochon and faceted. And although I have seen a good number of beautifully colored cabochon sapphires that are clear or mostly clear, they were cut on cabochon because they weren't perfect. But the ones that I'm most interested in, I think a lot of people are star or asterated sapphires. And I'm wondering if you could spend a little bit of time helping us understand the best way of grading and understanding the value of cabochon and star sapphires, please.
Yeah, I mean, the reason why gems get cut as cabochons is because they lack the clarity to be faceted. Faceted stones are almost universally more expensive than cabochon cut stones. And so the reason the stone gets cut as a cab is because it lacks the high clarity that would allow it to become faceted. So the very best cabochons are going to be the stones that are approaching facet quality. And what happens is when the stone is clean enough, it allows the light to pass deeper into the stone. And when there are longer light paths, then you have more absorption. And when you have more absorption, you have potential to have a more vivid color. And so the best cabochons will have what we call a glassy body. And let me see if I can find a picture of that. And so the glass body is the ideal. Okay, like this. Here you can see a superb, this is a sugarloaf cabochon from Kashmir. And this piece is actually in the Cornell Museum. And so it's on public display if anybody wants to go and have a look at it. But you can see the stone is very clear, and thus the color has the potential to be quite vivid. Now, star stones, you need to have inclusions in order to make a star. And this is the rub. Okay, here's a piece of carved sapphire. And it's really unusual to see carved sapphire, but you can see why it was carved, because it has too many inclusions to be faceted, or even too many inclusions to be cabbed. This is another example. This is a beautiful crystal specimen. This is in Bill Larson's collection. And it exists because it wasn't clean enough to cut. And so that's why you have that stone. And of course, sitting next to a beautiful faceted sapphire. But anyway, you asked about star stones. And let me see if I can find a section on that. And so star stones, they have the problem that you have to have enough silk in order to create the star. But if there's too much silk, you can't have a good color. And so the very best star stones will have just enough silk to create a star, and the star won't be very strong, but the color will be really nice. And that's the highest prices get paid for stuff like that. So here's an example of a fine star sapphire. Here are 3 stones of differing quality. Here you can see the stone is gray. That's because there's too much silk. And then you get, here it's a little bit better and the color gets a little deeper. And then here you don't have so much silk and the color gets far more vivid. And so the best stars are the stones that have just enough silk to create a star, but not materially affect the color.
And I know a lot of people try and sell star stones as being of high value, but I found sometimes they tend to ignore the dog legs or the broken arms of the star. And can we just talk briefly about the grading of the stars, if that's possible?
Yeah, I mean, with star sapphires, you grade color, number one. And so people will forgive a stone, like, for example, here, this stone, it's missing a leg here, okay? In this stone, the rays don't really stretch all the way to the girdle. That's not a problem because the color is good. And so the star is really secondary to the color. The best star stones have a really, really good color.
I remember seeing in the Detroit show a good number of years ago on the finger of Dave Wilbur, a
Yes.
beautifully perfect 50 or 60 carat star sapphire that on top and bottom, it had a good star, and it was just enough limpidity that you could see the good star on both sides, and it was had good color and a perfect star. And I thought, wow, that has to be really rare.
Yeah, I've seen that stone of Dave's, and it is a superb stone. And so that's the kind of thing where you have to look for that balance. You want just enough silk to make a star, but you don't want too much to affect the transparency of the stone, and because that affects the color. And so, I mean, I'll tell you honestly, the best sapphires I ever saw in my life were cabochons. And it was a pair of 10 carat stones. Each stone was 10 carats. They were perfectly matched, and a New York dealer was selling them. And when you flipped the stones over, they were sugarloaf cabs. And when you flip the stones over, they had been faceted on the bottom.
Oh,
And what happened, and they were in a Cartier mounting, I'm assuming that they had been produced by Cartier. And what apparently had happened is somebody had decided to take two faceted stones and cab the bottom. And normally that's a crazy idea, but these two stones, they were cashmere stones, and they were just the most incredible blue I've ever seen. I've never seen a faceted sapphire that had that, because it was blue all across the stone, the most gorgeous blue. And normally faceted stones, you know, you get these darker areas of extinction. And these stones were just blue all across the face of the stone. He was asking a pretty price for them. He was asking, I think, double what any sapphire had ever sold for at auction per carat.
how much was that?
It was a lot.
Oh,
I think he was, at the time, the record price for sapphire, my memory might not be correct, but I think the record price was 125,000 a carat of that stone that had sold at auction. And he was asking, I think, $250,000 a carat for those.
they were
worth it.
very rare.
They were worth it. Best sapphires I've ever seen. It was at a show, and after I saw them, I went and grabbed Bill Larson, dragged him over to have a look at them, and Bill agreed. These were just absolutely superb.
Yeah, one of those moments you treasure.
Yeah,
The
and they
other,
were perfectly matched. It was almost as though they had just chopped the crystal in half.
which is
they were
probably
absolutely
exactly what they did. Yeah.
Yeah, yeah.
So one of the problems, I guess, in grading also is, and I see this a lot. There's a new find in British Columbia where this has, I think, to this point, has proved a bit of a problem. Is that they have beautiful colored blue, but the zoning and the growth pattern in it is so gross in terms of the size of the of the zones that it almost looks banded. And so is there any sort of standards against which the size of the zoning or the fineness of the silk zones or in cabochons or in facet stones are a crucial feature in valuing?
Well, with zoning, and it also holds true for inclusions. I use this scale. Okay, I call it the distraction scale. Now you can imagine if somebody is smiling, and here's like a perfect smile, right? No problems. You don't see any problem. If their teeth are a little more yellow, well, that's not as good as this, but it's pretty good. You have a tooth missing at the back of the mouth. Well, that's a little worse, but it's still okay. You can't see it most of the time. Small gap in between the teeth. You see that all the time, but it's not that big. Chipped tooth right up front. Well, that's worse. Missing tooth in the front, that's really bad. You'll never take your eyes off it. And so it's like that with inclusions and color zoning. Is the zoning the first thing you see? That's not good, because that'll be the first thing you always see. And so unless it's a bicolor stone or something like that, that's not a good thing. So I always ask myself, how distracting is it? Can I live with that or not? If it's something that I immediately notice, then chances are other buyers are going to feel the same way about it. And so those are things you want to try to avoid.
Well, one of the tricks that cutters use that I've seen is they'll cut a stone oriented so that parallel to the table is a saturated color zone, so that the entire stone from the table on the top looks like it all has that color. And so I'm wondering if that is considered a distraction, or is it something that can look the other way on if the perception when you look at the stone from the top is of a fully saturated stone.
Yeah, there's a special category of stones in Sri Lanka, because Sri Lankan sapphires are often strongly zoned. And they call these stones otu. And the otu stones have color on the skin like this. And so there are a variety of ways that cutters can utilize that. What you talked about, they may lay the table along one of the pyramid faces, but generally the color suffers because the best color will be seen in sapphire. Best color is seen down the z-axis. In ruby, the orientation is not as critical, but in blue sapphire, the orientation is critical because the E-ray color is not nearly as fine as the O-ray color. And so sometimes they'll cut the stone with just a little bit of color right at the culet.
Yeah.
And when you face up the stone, you'll see it's all blue, but when you move your head off to the side or the other side, or you look at the stone from the side, the color washes out. And so that's obviously not a good thing. And so it's a question of degree. How bad is it? How distracting is it? And so all of those things have to be taken into account.
Yeah, clearly, one of the jewelry design tricks I've seen is they try and cover enough of the stone so you can't see below the layer of color. And so it appears from all that you can see above the setting to be a beautifully saturated stone.
Yeah. Usually these O2 type stones, this color zone is very deep in color. And so oftentimes, if you get too much of it, the stone will appear really dark blue or even black. And so that's something that you have to take into account as well.
Well, one of the problems in nature, as you and I both know, and everybody that I think that's been into geology and gemology knows, is that there's such a wide variance in terms of the quality of the stones and when they're first found. And yet a lot of these stones that when they're first found may only be pale blue, appear in the market as beautifully saturated stones. If the silk is rather coarse, all of a sudden they look, the silk is evenly distributed and it's a beautiful star. So I'd like it if you could take a few minutes here to talk to us about treatments that are being done, diffusion and heat treatments and so on, that actually are used to alter and improve the stone. And of course, which also has led to an awful lot of dealers saying this is an untreated stone or this is a treated stone. And if they're an honest dealer, they're also delineating what the treatments were. But unfortunately, not all dealers know what the treatments were when they get them. And I just hope that's something we can learn from you that'll help us understand it.
Okay. In terms of corundums, the earliest treatment took place in Sri Lanka, and it was going over 1,000 years ago. The reason we know this is because there was a scientist named El Biruni, and he perfectly described how the treatment was done. He said that you have to put the stones to be treated in a shell, and you have to heat them up to the temperature at which gold melts. And so we know the melting point of gold. And so we know that it was about 1100 degrees, give or take. And they had discovered probably long before that, that if they heated the purplish stones, they would become more red. And so that was the earliest heat treatment that we know of. And that's over 1,000 years ago. Then as chemistry developed and furnaces developed, higher temperatures were possible. This really came about because of people trying to synthesize ruby. And so once they got the technology where they could melt corundum, then they decided, well, let's take little bits of corundum, little bits of ruby, and try to melt them together and make a larger stone. And so that all happened in France in the early 1800s and through the 19th century. It eventually led to the first synthesis of ruby, and that happened also in France in the 1800s. And so this was really the birth of modern heat treatment. Eventually, someone discovered that if you took a sapphire and heated it high enough, that you could clarify it, and you could actually dissolve the silk. And so, while these treatments originally they started out with charcoal basically, eventually they developed, and this is an example of the Sri Lankan treatment. You can call it the El Biruni treatment if you want. These are the stones with blue patches in them, and after heating to about 1100 degrees, something like that, you can see the blue is mostly gone. And so they've improved the color of the stones. Now they also found that they could lighten the color a little bit of darker blue sapphires. And that was something that was discovered and reported on about the turn of the 20th century. And so that was the next step up. The modern heat treatment, which we call Gyoda treatment, requires temperatures of about 15 or 1600 degrees. And so that kind of treatment required better furnaces. And that happened later in the 20th century. They take stones that have what they call in Sri Lanka a gyoda or a diesel appearance. You can see there's an oily appearance when the stone is over a light. And so the dealers would look for this diesel. That told them that stones could be treated. So they'd start out with material like this, and then it could be turned into clear blue stones like this. And so that was really the modern era of heating. It started in a big way in the 1970s in Thailand. Thai dealers would go down to Sri Lanka and buy this Gyoda material that was very inexpensive because it was not of high enough quality, not good enough color, and they would heat it and turn it into what looked like fine blue sapphire. And so that became a real boom. And after that material got into the market, then dealers decided, well, what else can we do? And they started experimenting on everything because huge fortunes were made heating Gyoda sapphire. And this eventually led to diffusion treatment. Diffusion treatment's a little bit different. This diffusion process was actually started by Union Carbide in the United States. During World War II, or prior to World War II, the US government declared that sapphire, synthetic sapphire, was a strategic material. It was necessary for certain kinds of things, certain kinds of tools, and windows on instruments and so forth. And so all of the synthetic corundum was largely being made in Europe at that time. And so they asked Union Carbide, which is a big industrial corporation, they asked Union Carbide if they would start growing corundum. And they did that. And one of their workers at one point noticed one of the bulls that they had grown had a little patch of silk in it. And he knew what silk was. That's how you make a star sapphire. And so he did a number of experiments, and that company, the division of Union Carbide called Linde Air Products, eventually patented the production of synthetic star sapphires and rubies. And with the sapphires that they were growing, they had a hard time getting the color even. And so they actually figured out a way to make the color even by diffusing titanium under the skin, into the skin of the stone. And so Union Carbide was the first one to do titanium lattice diffusion. And let me see if I got a picture of that. And so this is what that involves. You pack the stone in a titanium powder and you heat it as close as you can get to the melting point without melting the stone. Corundum melts at 2040 degrees. And so you want to heat it up to maybe 1800 degrees, 1900 degrees. You can't go much hotter than that because usually your furnace will start breaking down and you may melt the stones. And so, and this is from the original Linde patents about how they did it. And so that was the first titanium diffusion. But Lindy didn't do this on natural stones. Eventually, a company in Europe bought the patents rights from them and started diffusing natural sapphires with a light color. And they actually didn't tell people what they were doing. Eventually, they got caught, and it was a kind of a scandal. I talked to one man who worked at the company, and he said, yeah, it was one of the dark chapters in the company history. But anyway, so the titanium diffusion, bulk diffusion, actually started in the United States, spread to Europe, and then came to Thailand. But the Thai cookers, they were trying everything they could, and they eventually, one guy, he was getting a lot of material from Madagascar, and he was cooking the stuff, and he noticed one stone came out a brilliant orange color. And he traced that back to the piece of chrysoberyl that had been in the burn in the crucible. And chrysoberyl contains beryllium, and he would buy up chrysoberyl and crush it, and he would diffuse the stones that way. And eventually they figured out they could use beryllium powder. And so that started the whole beryllium diffusion thing, which was also a dark chapter in Thai history, Thai gem trade history, because they did not tell people what they were doing. And so they were producing what looked to be Padparadscha sapphires at very inexpensive prices. And they came within an eyelash of destroying the Thai gem industry because of the scandal that happened. Beryllium.
Just a quick question, if you don't mind.
Yeah.
The diffusion process, is it done on cut stones, on rough, and how deep into the stone does diffusion actually progress from the surface?
Okay, so for titanium diffusion, the depth is very shallow. You can't get much penetration because the titanium ion is too big. But beryllium is a very light element, and so with beryllium, you can diffuse it deeper into the stone, and if you heat the stone long enough, you can diffuse it all the way through a cut stone. So what they were doing,
the titanium process is done on an already cut stone, is it?
Yes,
because it's
that's
so shallow.
correct.
Okay, thanks.
Yes.
That's what I was trying to clear up.
Yeah. Now, generally, with the beryllium diffusion, they also want to do it on faceted stones, and then they'll repolish them. Everything needs to be repolished because the surface gets destroyed. And so what they want to do is they want to diffuse the beryllium into the stone. It creates a trapped hole color center that creates a yellow or orange color. And you do that on a pink stone, and suddenly you have a Padparadscha sapphire.
Yeah.
And so that material came out in a huge way in the year 2000, 2001. And it was eventually through the work of John Emmett and Ken Scarrett, among others, myself included.
We've lost you.
And so that material nowadays, you can still find the stones in the market, and that material is actually cheaper than the starting material that they started with because the price crashed so much.
Wow.
So now you don't see it because the original pink sapphire is worth more than the treated Padparadscha sapphire.
That I was told at one point that some people are using the one of these treatments, like a heat treatment, to almost melt, if not melt and recrystallize the inclusions in the star stones to give them a cleaner and more well-distributed silk. Is this also what's going on, or is that just something I heard it wasn't?
Well, it is possible to diffuse titanium into a sapphire, and then if you do it in the right way, you will create silk under the surface of the stone. And that titanium, it's a titanium diffused star.
Yeah.
It's not that difficult to identify. I don't know if I have a picture of that or not. Just getting back to the beryllium treatment. So this is the original starting material, this pink sapphire from Malacca. And this is after beryllium diffusion. This is sapphire from Songea in Tanzania after beryllium diffusion. And so you can see what it can do. In terms of the diffused star, I really can't remember whether I have a picture of that or not, but it creates a star just on the skin. Yeah, here it is. Here it is. So this is a titanium diffused star. And with experience in the microscope, you can recognize that the silk is only on the skin and just beneath the surface.
Okay. So do you have any images of what you consider to be the world's best sapphires?
Well, as I said, the world's best sapphires that I saw were this pair of stones. And so, yeah, I mean, we do have images of fine sapphires in this book. This is a big stone, 392 carats, that sold at auction from Sri Lanka. Whoops. I've shown that already. Here's a fine sapphire. This one from Burma. This is a beautiful crystal. And I think Jolion's probably going to get excited about that one.
Also, what I.
Yeah, and here's a little bit
I'm
lighter color. Here's a fine star sapphire.
How big is that one?
That one is 50 carats. So there are, there are fine sapphires. I mean, I've seen, you can get big sapphires of fine quality. You never get big rubies of fine quality. So I've seen some spectacular sapphires of 100 carats or more. For ruby, it's extraordinarily rare to get a ruby of really top quality of even 3 or 4 carats.
Yeah, so that makes
And
it
when
a
you
lot.
talk about 5 carats or more, then it becomes crazy rare.
Yes.
And if it's 10 carats or more, it's just insanely rare. So
These are gemological descriptors, are they?
yes. And so that's the nature of the material. You do get big star sapphires, and you do get big faceted sapphires. The biggest star sapphire I ever saw was a piece that was shown to me in a vault in Hong Kong that some Sri Lankans were trying to sell. It was not the number 1 color. It was probably the number 2 or 3 color. But in other respects, it was absolutely perfect. It was huge. I think it was 300 carats or something like that. It was perfectly cut. And it had a razor sharp star. But as I said, the color was not the really vivid blue. It was more of a sky blue, but for the size, I mean, my God, it was amazingly perfect for a stone of that size.
Always a joy when you find one of those or get a chance to see them. And I think
Yeah.
I've been lucky seeing stuff like this at the AGTA every year. You wander
Yeah.
around, someone will pull something out of their pocket to show someone, and you just happen to see it and say, "Whoa, that is
Yeah.
amazing!" And they show up out of nowhere. And so
Yeah.
some of
I
them
mean,
are
that's what makes this business interesting, isn't it?
I agree. Well, I really appreciate you giving your time, sharing it with us. I know you're a very busy man.
Oh, my pleasure.
I'd like to thank you very much on behalf of our group with GemQuest. And I'd like to ask you if you just tell us, and it's not a commercial here, but you do have the most authoritative book out in print right now that I know of anyway on sapphires, rubies. Could you please tell us the title and how we could get one for those who want
Yeah.
to know more about than we've been able to do in this short amount of time?
Yeah. we have a few books. The latest book is called Ruby and Sapphire, a Gemologist Guide. And that book is, let me just scroll forward a little bit. That book is available on our website, which is lotusgemology.com. And we have another book called Ruby and Sapphire, a Collector's Guide, which is more for collectors. The Gemologist Guide is more technical for working gemologists. Collector's Guide is more for collectors and lay people, more of a coffee table style book. But all of those are available on our website, which is lotusgemology.com. And you know, for the Gemologist Guide, get it while you can. It's almost out of print. And my earlier version of this book from 1997, once it went out of print, the prices skyrocketed to $1,000 or $2,000 a copy. So if you're interested in this, you want to get this book, now's the time to get it.
A final question. Because of all the tricks of the trade that are now being applied to sapphires over the years, do you really need very specialized equipment to do this? Like, do you need to be a more sophisticated lab to really find the tricksters and the simulants, or can you get by with simple equipment?
The days, you know, when you could get by with just a loop are long gone. I had to explain that to a Bangkok dealer who had 40 years of experience. And I was telling him that, you know, there are people in the bush in Madagascar treating sapphires. And so you can go to Alakaka and buy the stones there and they still may be treated. And he said, well, what are we supposed to do? And I said, well, this is it. You know, this is the world we live in. And so what's actually happening is the people who are treating stones are actually taking greater steps to avoid disclosure, because the price difference is great between a treated and natural sapphire.
Oh.
And so they're actually reducing the temperatures now, because the high temperature heated material is fairly easy to spot. And so what they're trying to do is reduce the temperatures enough to avoid detection. And so, yeah, the days when you could do things with a loop or even with a microscope alone, those days are gone. Now, you know, with beryllium diffusion, it requires extremely expensive equipment to identify.
Yeah, so buyer beware. And I think I'm going to end this now, if that's okay with you. People realize that you're on the far side of the world, and the time zone difference just didn't make it convenient for us to be able to do this on the time that we normally do our program. So this is a recording. I tried to act as if I was the audience asking questions they might want to know answers. I hope
Yeah.
I did a sufficient job to bring your knowledge to their attention.
Well, I want to thank you for getting up at 3 in the morning to do this.
I just stayed up, Dick.
Well, anyway, I'm sure you're ready for bed now.
Oh, very much so. And thank you very much. And I hope that our audience will very much appreciate your great knowledge and experience that you've shared with us over this time. And I hope you have a good day.
Okay, thank you.
Thanks, everybody. Well, that was, I hope, very informational and interesting for you all. Dick's an easy kind of guy to listen to, and he gave us a lot of information in a very conversational way. I hope it helped everybody gain a bit of knowledge in terms of understanding the gem sapphire. But to finish things off, I am in the debt of a young lady who is the gemological curator for the British Museum of Natural History. I hope I've got the name correctly. And so I'm going to ask to be allowed to share screen and show you a few slides that were made from the museum in London to close things off.
Okay, all ready for you, Ray?
Yeah, oh no, that's not it. Oh dear, what have I done here? Not it. Give me a second, sorry. There we are. So thanks to Robin Hanson, I was able to have access to a few of the very interesting sapphires in the collection of the British Natural History Museum. The first one here, BM 89467, is actually a rather large button that's carved out of rock crystal, and was from the original collection that formed the museum way back in 1753 in the Sir Harry Stone collection. And the sapphire in the middle is 31.5 carats. So you get a sense of the size of this button. And if this was a button worn on clothing, I would have to imagine that you'd have to sort of lean forward wearing a piece of clothing with something like this on it.
I think you've got the wrong thing shared, Ray. We've just got a single image at the moment.
Well, it's showing, how do you mean?
There was the. Is this not meant to be a PowerPoint presentation?
Sorry, what?
This is not a PowerPoint presentation you got shared at the moment.
Okay.
It's just a single image.
Okay, so sorry about that. I don't know how that happened.
That's better.
It is?
Yes,
Right.
now we see what you're talking about.
Okay, awesome. I don't know what the difference is. It did exactly the same thing. So in the last video, it was interesting that we spent a second looking at this particular carving with Richard Hughes. And it's a BM 14953. It's a carving of an idol or Buddha, probably, and it was later, it looks like later mounted onto a stick pin, which is a very common thing in Victorian times. And it was purchased by the museum in 1842. So we've seen this thing 2 or 3 times today, thanks to the book that was shared, pictures in the book that was shared by Richard. Oh no. This is an interesting stone. It's got 12 rays, and when you're looking at the crystallography of sapphire, the normal would be to have 6 rays, but there are inclusions within the structure of the sapphire. The titanium or the rutile inclusions will give you the 6-ray star, but in this case there are also iron inclusions, and they give you the three rays of the golden colored rays. So you actually have 2 different colors of sets of rays in the stone. And of course, here you can see very distinct zoning. So if this was something that someone was trying to sell, it might have you might sell it on the basis of the star, but you'd have to back off in terms of the quality of the silk distribution. And the picture, as you can see, was done. It was acquired in 1993 by the museum, and the picture was done by Robert Weldon, who obviously is a talented photographer. Now, this is interesting. This shows a little bit of the range of Padparadscha, as was discussed when Dick was talking about this. And the 54811 on the left is a clearly predominantly pink stone. I actually would have called that a pink sapphire, but that's just me. And the one on the and it was 9.35 carats, and the one on the right is actually closer to what I've seen most often to be called Padparadscha. It's sort of an orangey, pinky brown color, and it's 57 carats, which means it's a sizable stone. And again, nicely captured by Robert Weldon. But I mean, this shows some of the problems that are created in the trade with terminology, and of course the consequent pricing that's associated with terminology. The next shot I think is interesting because this is showing what I was asking Dick about, is the sort of the tricks of the trade that are done when you're cutting. And so you can see this stone has transparent blue and yellow zones in it on the side, but from the top, it looks like a predominantly almost electric iron blue stone, and the color looks relatively evenly saturated. Although you can see a slight hint through the table of a yellowish brown culet, but I just think that this is one of the things that you really have to be careful of when you're buying stones, is if you're hoping to get an evenly saturated stone, it isn't always what it appears to be when you look at it from the top. And the file stone BM 1913-301 gives you a clue. It was purchased in 1913 by the museum, and it's a 14.18 carat stone, and it's quite lively, but it's in the lighter color range of what would be called blue sapphire. And I think I found in the past when making jewelry that the darker the sapphire, the harder it is to sell, and the livelier and lighter somewhere between this tone and the darker tone seems to be the ideal range of blue that people find to be the most valued in their eyes. So, and again, as you know, beauty is in the eyes of the beholder, and especially when it comes to selling expensive precious stones like sapphires, color is everything. And so this is a nicely cut and quite lively looking stone. And this ends the presentation that we have today, and I'm hoping that everybody that came learned something that they didn't already know, or they learned more about things they already knew, so that they'll walk away being absolute experts on the subject of sapphires. And I leave you with the thought that next month in October, we'll be getting together again on the last Sunday, which happens to be Halloween. And I may show up in a mask and in a costume, who knows? But the stone we're talking about masquerades, as some stones have been known to do, as other than itself, and that's spinel. And I'm hoping that from amongst you all, you can throw to me some leads for some interesting and exciting presenters on the spinel family of gems. And I leave you with that, and I hope you all have a great evening or day, as it turns out. And I hope that this has been a good program for you. And I'll take my leave and thank Jolyon for his contributions and assistance, and thank you all for sharing your time with us today.
And thank you, Ray.
And I think we'll close things off, and I hope you all have a good day.
Okay. Goodbye, everyone.